Hello everyone. As we work into our last week here, I just want to take you through how we can find the vector equation of a line, and then our last lesson we'll look at how we can find the vector equation of a plane. So in our note here, what I want to start out with is just a quick reminder that we have equations of lines in 2 space or in 2D. We have our slope y-intercept form, so y equals mx plus b. We also have our standard form, which we don't use quite as often, but we did look at this back in grade 9. And those are the 2 main forms that we work with. There's a few others out there as well, but these are the ones that we learned about through our high school career. And remember that the goal of any equation here is to try and describe any point that's on the line. So if I have an x and a y coordinate, I could sub that into this equation, and we could then figure out what are all the points that are on that line. Similar with if we're writing this in standard form, which is really just this equation rearranged into a different form. We're going to look at it today as a different way, completely different way that we could then describe the points that are on this line. And remember, that's the idea then of an equation, is how do I describe all these points? And we're going to describe the collection of points on this line using vectors, or we call this our vector equation of a line. So to describe any point B with coordinates x, y on a line, so for a visual, I'm going to put that point here, but really that point B could be anywhere on that line. We need a couple of things. First, what we need is that we need some initial point that is on the line. And this is very similar to the idea that if we had slope y-intercept, we have an initial point. Specifically, we have the y-intercept. Here in vector form, we're saying, well, let's have an initial point on the line, and that initial point could be anywhere on the line. So I'm going to say, well, let's say here is that initial point with coordinates x naught and y naught. That would mean that I could then draw a position vector. Remember, position vector is just a vector from the origin to that point on the line. And this is really how we use vectors to describe points on lines. If I have a position vector, then the components for this vector are the exact same as the coordinates for this point. They are the exact same ordered pair. So this point on the line is the same as saying, well, I have a position vector that's pointing to that point on the line with the exact same ordered pair in both cases. What we now want to do is, if I have a vector that points to this initial point, I now want to be able to point to any point that is on the line. So for instance, I would want to, in a very similar way, be able to point to this point here that is on the line. So how can I create a vector that will point to any point on the line? Well, we have this initial point. The next thing that we need is what we call a direction vector. A direction vector is just a vector that points in the same direction as this line. In other words, it's a vector that is parallel to that line. So I'm going to call that D. So I'm going to draw that down here and say, well, here is our direction vector, a vector that is pointing in the same direction as that line. And what we should see from this then is that I can actually get from this initial point to any other point on the line by using some multiple of this. If I look at this vector D, it's almost the same distance as this, not quite as big, so I would have to use some multiple of this D. In other words, I'm going to say T times D. I don't know what that multiple is, but I'd have to use some multiple of that direction vector, and that would get me from my initial point to any other point that's on the line. If T was negative, that would point to another point B down here. If I made T really big, we would have a point that's way off the graph that I've drawn. If I've made T really small, that would point to some B value that is here. So as long as I have a direction vector that points in the direction of the line, any multiple of D will take us from this initial point to any other point that's on the line. And that's what this part here is saying. Vector AB, to get from A to B, would be then some multiple of D. And then our bigger conclusion is this then. If I want this position vector OB that points to any point on the line, well, we can now use our vector addition to do that. I can move from the origin to my initial point using that initial position vector, and then I can move from that point to any other point on the line using AB, or as we saw here, some multiple of that direction vector. And if I can create this vector OB is a vector that will point to any point that is on the line. In other words, it is describing every single point that's on the line. So that's our conclusion here. Now that we can use this idea to describe any point. If I want a vector OB that points to any point on the line, in other words, it's going to have the exact same ordered pair as the point, then what I can do is I can first go to the initial point, okay, using vector OA, our vector addition. So this vector plus vector AB, and to get from A to B, what we're going to do is take some multiple of our direction vector. And our direction vector had components A, B. And that's it. That's how we get our description of that point B. So our vector equation of a line, if we try to write this out in general, is that we need two things. I need an initial point on the line, and I need a direction vector that's parallel to the line. In other words, it has the same direction as the line. And then we can write our vector equation. We often use R here for our resultant. Would be first we move to that initial point using the position vector, and then we would move some multiple of our direction vector up and down the line. So some multiple of that direction vector. We can also write it this way. If we want to write this as an ordered pair, our resultant xy would be our initial point, or our position vector to our initial point, plus some multiple of that direction vector. If that seems confusing, in a second we'll do an example. But before we get to our example, what I would like to do is then say, well, the same way that we have slope y-intercept form, and we can rearrange that to different forms, we can do the same thing with a vector equation. This is initially how I would write this vector equation, but we can also write this in what we call its parametric form, or parametric equations. Essentially, all that is going to do is take the x and the y and separate them. So we can write this as the x component would be x naught plus a times d. Okay, that's how we're calculating the x component here. And the y component would be y naught plus bt. And in this form, what we see is that here is that initial point. And here is our direction vector. And what we have here is this value t. The reason we call it a parametric equation is t is called a parameter. So you can put whatever parameter you want in there to create points on the line. And again, we'll look at that in just a second. The last version that we have is what we call our symmetric equation of a line. Basically, this now takes this form and says, well, let's isolate for t. So if I isolate for t in this first version, I would have x minus, okay, x naught all over a. And if I isolate for t in this version, we would have y minus y naught all over b. And since in both cases we have isolated for t, then those two things would be equal. And what we should see in this version is that we have here is our initial point. So x minus the x-coordinate from the initial point, y minus the y-coordinate from the initial point, and in the denominator, this is where we have our direction vector. And again, this is a lot of theory on this first page, so if you want, rewatch the video or listen to the explanation again, take a second to read through that. But what I'm going to do now is jump ahead to an example of this, and sometimes when you see the numbers, this starts to make a little bit more sense. Okay? So here it is. Find the vector, parametric, and symmetric equations of a line through these 2 points. So similar to something that I would ask you in grade 9, other than I wouldn't ask you for vector equations, I would ask you for, say, slope y-intercept form. And we'd be trying to figure out, well, what is the slope, what is the y-intercept? And we've done that a lot in our 4 years at high school. So it's that same idea. If these 2 points are on that line, how can I find the vector equation? So what we need to do this are two things. We need an initial point that's on the line. Well, essentially we have two initial points. We have this point and this point here. So you can pick whichever one you want. I'm going to pick this one only because it has no negatives. But you're welcome to pick either of them, and both would be fine, and both are correct for this equation. The next thing that I need is a direction vector. I need to know what direction is this line pointing. And since these 2 points are on the line, the easiest way to get a direction vector is just to figure out, well, what is the vector that goes from A to B? So remember that if I want to calculate a point-to-point vector, all we do is subtract coordinates. So I'm going to do 4 subtract -5. Then I'm going to do 5 subtract 2, which gives us a direction vector of 9, 3. And the important part is to remember that with vectors, we can always reduce them. So I'm actually going to reduce this vector and say, well, this is the vector that goes from A to B, 9, 3. That is perfectly fine for a direction vector, but why not use its reduced form? So if I divide them both by 3 and say, well, this is pointing in the same direction as this, and both of these are pointing in the direction of this line. So I'm going to use that reduced vector instead. So if we want our 3 forms then, our vector equation is then as follows. Our initial point that's on the line, which is 4, 5, plus some multiple of that direction vector. If I want the parametric form, then all we're doing is separating the x's and the y's. So the x coordinate is 4 plus 3t. The y coordinate is 5 plus 1t, or just t. If I want to write out the symmetric form, you can either memorize the form from the previous page, or what you can think of again is how we develop them. Symmetric really just means that I'm going to isolate for the t. So if I isolate for the t here, I'm going to have x minus 4 over 3. And if I isolate for the t here, I'm going to have y minus 5. If you want, we can say over 1. We don't really need it, but there it is. So there's a symmetric form. Some students like to just rearrange it from parametric form. You can also memorize it that there is the initial point. So x minus the initial x coordinate, y minus the initial y coordinate, and there is our direction vector 3, 1 from here. So it's up to you which way you feel more comfortable doing this. If you want to see how is this describing points on the line, I'm just going to put here a little note on the side. How does this actually generate points or describe points that are on the line? Well, we generate points or describe points on the line using this parameter t. Notice here that if t had a value of 1, that actually generates a point here. I can either do that here or here to see this very easily. If t is 1, then my x coordinate would be 4 plus 1 times 3. In other words, my x coordinate is 7, or you can see that calculation here for the x coordinate. If I want the y coordinate, same idea. I would do 5 plus 1 times 1, okay, and that would generate a y coordinate of 6. If t is 2, same idea. We could do 4 plus 2 times 3, or 4 plus 2 times 3, doesn't matter where you do it. We would end up with 10. And for my y coordinate, 5 plus 2 times 1 would generate then a y coordinate of 7. T could be a decimal, t can be any real number. I'll do one more here. Okay, if I change t to a negative number, let's say t is -3, we could do the same thing. If t is -3, then I would have 4 plus 3 times -3. That would give us -5. And my y coordinate, 5 plus -3. Again, here or here, we're doing the same thing. Would give me a y coordinate of 2. So by changing that parameter t, we are actually describing all of the points that are on this line. And again, that whole visual is that graph that we initially did. Starting at the origin, we move to this point, and then we move up and down the line. This is the direction of the line. We move up and down the line, some multiple of that direction vector, and that will move us to points up and down the line. And using vectors, then we can describe all of the points that are on the line. Second part of the question, Jin just says, well, using this equation then, is the point B 13, 8 on the line? So what we can do is then test. I can say, well, the x coordinate is 13. So I'm going to use the parametric form here. I'm going to say, well, if I sub that into that parametric form and I solve here, I'm going to get 9 is equal to 3t, or t is equal to 3. In other words, to generate this x coordinate, we need a parameter value of 3. What I need to know is, am I using the same parameter to generate that 8? Okay, in this equation, I can't have different t values for the same point. Okay, one t value should generate 1 point. So we figured out to get the x coordinate, the parameter has to be 3. So then I'm going to test, well, what happens with the y coordinate? And if I look at the y coordinate, what we find out is that the parameter here is also 3. In other words, a parameter of 3 in both cases will generate the correct x and y coordinate. So that is saying then, therefore, this point, 13, 8, is on the line. Now, the nice part about this vector form for a line is that now this easily extends into 3 dimensions. Our slope y-intercept form and our standard form for a line do not extend into 3 dimensions. However, this vector form now does. I'm not going to redraw the picture. It's basically the same picture we did in 2 dimensions, other than now we're going to extend that line into 3 dimensions, but it's the exact same idea. I start at some initial point. We can now start at that initial point in 3 dimensions. I'm going to move up and down the line using our direction vector. Our direction vector now has to have 3 components, since we are now going to move in 3 space. And if we do that, then in 3 space, it's not a big jump here to say then our vector equation would be x naught, y naught, z naught, plus some multiple of that direction vector. And again, we just use that parameter t. So very small extension, and we're now in 3 space, and we're describing lines in 3 dimensions. We can break them all apart. The only difference here is we now have 3 parametric equations, x naught plus at, y equals y naught plus bt, but we also have a z coordinate now, as we describe this line in 3 dimensions. So now we would have z naught plus ct. And for each of these, if I isolate for that parameter t, I would have x minus x naught over a. If I isolate here, I'd have y minus y naught over b. And my last one, if I isolate for t, I would have z minus z naught over c. And there's the same 3 forms that we just looked at, but now looking at this in 3 dimensions. We have an extra parameter here, we have an extra component here, and now we have all 3 pieces here for our symmetric equation. So same type of example that we just did, except for in 3 space, just so we can see how this works. So same idea, I need an initial point. Pick whichever one you want. Okay, I'm going to pick this as my initial point, 3, 7, 1. My direction vector. Then will be the same idea. If I have 2 points, I can say my direction vector for this line is the same as from A to B. I'm not going to show all the calculations this time. We'll just do them. 6 minus 3, 2 minus 7, 1 minus 1. There's our direction vector for this line. And then we can say, well, here's our 3 different forms. My vector equation is initial point 3, 7, 1 plus some multiple of that direction, 3, negative 5, 0. My parametric equations, the x coordinate is 3 plus 3t. My y component then is 7 minus 5t, and my z component would be 1 plus 0t. We don't need the 0t. In other words, the z coordinate will always be 1. And then lastly, symmetric. If I end up isolating then for t, I would have x minus 3 over 3, which is equal to y minus 7 over negative 5. And we end up with an interesting scenario on the last one. Normally I would have a third piece here as I isolate for t here, but because there is no t here, what we do instead is we can't actually isolate for t, so instead of having 3 fractions, this is a unique example where I just leave that as z equals 1. And there's our vector equations for lines in both 2 and 3 dimensions. Now, last piece that I want to look at is I want to come back to our standard form, ax plus by plus c equals 0. And this is going to be important as we lead into our next note on the equation of a plane. Keep in mind that this now goes back to 2 space, so R2 only. Okay, this does not work in 3 space. We do not have a standard form or a slope y-intercept form for a line in 3 dimensions. We only have that vector equation for our lines in 3 space. So we're back to 2 dimensions only here. And what I want to define here is what we call a normal vector. So a normal vector is any vector that is perpendicular to that line. Okay, so if I'm picturing here then some line, I actually have 2 vectors that are really important with that line. One is on this line I would have, that's hard to see, I know, but I have some direction vector. Our normal vector then is perpendicular to that line. So there is that normal vector. So for example, if I had some line that had a direction vector of 2, 3, and a normal vector of xy, well, what we would know then is because these two are perpendicular, this is where we start to see some of those previous skills come out, that would tell us then that the dot product between these two must be 0. Remember, the dot product is 0 if I have 2 perpendicular vectors. That means that if I have 2, 3, and I do the dot product with x, y, that must be 0. In other words, 2x plus 3y must be 0. So how do I get a normal vector from this? Well, I'm going to say, therefore, let's choose one of 2 normal vectors. These are really easy to find. If I want this to be 0, what I can do is just switch these coefficients. If I make the x value 3, and I make the y value 2, I would actually have 2 times 3 is 6, 3 times 2 is 6. I wouldn't get 0, so what I need to do is just make one of those 2 values negative. So I'm switching these around and just make one of them negative. And now I would have 2 times 3 is 6, 3 times negative 2 is negative 6, and that gives us 0. So it's a really easy way to find a normal vector. I'm going to say, or the other one, we said let's switch them and make one negative. It doesn't matter which one you make negative. So I would probably choose one of those 2 as my normal vector, where I've just taken my direction vector, switched them, and made one of the 2 components negative. And we'll just make note of that here on the side. So say switch components of our direction vector and make one negative. Now, why am I talking about a normal vector? Well, if we come back to that standard form, we have a really interesting result that occurs. If I have the standard form, by the way, this is also referred to now our scalar or Cartesian equation of a line. So if I'm given this here, our standard form, a normal vector to this line just happens to be a, b, and not just random a, b, but we're talking about the coefficients from those first 2 terms. So our normal vector would be ab. So all along here, when we've had that line in standard form, we've actually had a vector ab that is actually perpendicular to that line. So If I come back to then, given some vector equation, okay, this is actually from our first example, the one that we found, I'm going to say let's determine the scalar or the Cartesian equation of that line. So if I look at this equation in its vector form, we have an initial point, that is 4, 5. I have a direction vector. I'm not calculating it this time, I have it, it's sitting right there, so my direction vector is 3, 1. We also have a normal vector. So my normal vector would be, well, let's switch the order here and make one of them negative. In this case, it doesn't matter which one, so I'm going to use my normal vector as 1, negative 3. That means that if I want to write the scalar equation, Cartesian equation, or as you are probably more familiar with it, called our standard form, we can now say, well, now I know that the a value is 1, the b value is negative 3. The only thing I don't know is what is that c value in that form. However, we have an initial point, so I can sub in for x and y, that initial point 4, 5. If I do that, we have 4 minus 3 times 5 plus c is 0. 4 minus 15 give us negative 11. So if we rearrange, c is 11. And therefore my standard form or my scalar form or my Cartesian form, whichever name you want to use here, x minus 3y plus 11 equals 0. Okay, so there's all the different versions that we can use. Keep in mind that the vector equation in its 3 different forms works in both 2 space and in 3 space. However, that this form here, our scalar Cartesian form, only works for lines in 2 space. We're going to come back to this idea in 3 space, but it actually represents something a little bit different. If you have any questions, again, please let me know. Send me an email, and I'll give you a hand with anything that you need. Have a good day, guys.